Hi, everyone. Welcome back for Chapter 7. In Chapter 7, we are going to begin doing a thing we're going to be doing for the rest of the semester. That is, we're going to be using data and data that was collected through polls or surveys or experiments as a way to estimate and talk about population parameters. Our first example we're going to take a look at is about estimating a population proportion. And remember, population proportions are usually some sort of percent, like, 35% of the population supports, I don't know, whatever it is they support, Article 1. TIC, Article 1 of something. Or since we're heading into an election season this fall, 35% of the voters support candidate A or candidate B or whatever candidate it is. But that sort of thing. What we're going to do is we're going to have a question about a population proportion, right? Like what percent support this, or what percent don't support this, or what percent have dogs, or what percent don't have dogs, those sorts of things. And then our question is, how can we gather data and get a reliable estimator for that population proportion, right? All right, so the key concepts here we're going to be taking a look at. Key concepts in this session we're going to take a look at are how we're going to use a sample proportion to make an inference or a prediction, if you will, about the value of that corresponding population proportion, right? We're going to address something called a point estimate, right? The point estimate is the estimate that we're going to find through our data collection, right? The estimate we're going to find through our data collection, our point estimate, is going to be our p hat, right? Our sample proportion. And then from that, we're going to build something called a confidence interval around that sample proportion. And our whole goal here is that hopefully that confidence interval will help us identify a true value of a population proportion. And then we'll take a look at how sample sizes can affect that and how we could reliably predict what sample size we would need to get a certain level of accuracy, right? Now we're going to use sample proportions here. That is, we're going to gather data and create a p hat, a sample proportion, because it is a reliable estimator, an unbiased estimator for our population. All right, so let's take a look at an example and see what's going on here. Right. So a Gallup poll was taken. So a poll was taken of which 1,487 adults, that is our sample size N is 1,487, were surveyed, and 43% of them said they're still holding on to a Facebook page. Right. So we got a 43%. Now, where did 43% come from? Well, it came from our sample. That makes that our sample proportion, or in terms of the language of statistics, that our p hat is 0.43, that 43%. Right? So based on this results, we have a pretty good point estimate, right, of the true proportion, the population proportion p of adults who have a Facebook page. It should be somewhere close to around about 43%. And one thing to keep in mind here is we are going to go with the assumption that that was done correctly. That is, that this poll that was taken was a simple random sample, blah, 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 blah. All of the necessary requirements for this experiment were met. So we're never going to try to make the argument, oh, it's wrong because they sampled wrong. No, we're going to, in these examples, we are going to assume that whoever set up this experiment, or in this case, this poll, did it correctly. Right? And so our job here then is we want P, right? We want the population proportion of adults who have a Facebook page. This is virtually impossible to know, because to know that value means that we would have to talk to all adults in our population and ask them, do you have a Facebook page, yes or no? And that's just not going to happen. So we estimate it. And how do we estimate it? We get a sample from our population and we ask them. And then they give us a point estimate. They give us a sample statistic, in this case, a sample proportion of 43%. And then we try to make the argument that 43% should be close to that population parameter P that we wanted. That should be close to, right? That those numbers should be a reasonable, it should be a reasonable match. Right? Now what we're going to do to make our estimate a little better is we're going to build something called a confidence interval. Now you've seen these before, but it's doubtful that you ever actually have heard them referred to as a confidence interval. A confidence interval, or an interval estimate, is when we take that point estimate and turn it from a single number into a range of values by adding and subtracting a little bit, which we refer to as our margin of error. So what we'd like to do is we'd like to create a little bit of wiggle room in that estimate for that population proportion. So rather than saying it's exactly 43, we would say it's close to 43 and here's how close it is. Now, the problem with that is, right, here's 0%. Way over here is 100%. Now, I don't know what P is, but I'm just going to put it right here. Let's just say that this is truly P. And then I went and got my sample proportion, which we said was P hat, and it was 43%. I'm trying to use this to estimate that population proportion P, but it's most likely going to be off. It's probably not going to hit P exactly. So what I do is I build a little bit of an interval around it. And let's just for argument's sake say that our sample was a little high, and that's where P hat is, right there. It's close, it's a pretty good estimate. But if I did this and said, rather than just 43%, let's make a little interval around it. And let's say that that's going to be our interval estimate for P, our 43% plus or minus a little error, a little margin of error E. And we'll worry about how big E is later, right? I'm going to get a better estimating tool. I'm going to get a tool that estimates better, right? Now, if I made E larger, I would just get a larger interval. And a larger interval has a better chance of actually matching where P really is on that number line, but a larger interval also makes that value less useful. And what I mean by that is this. If I was able to tell you that it was 43% plus or minus 2%, well, that's a pretty small margin of error, and I would feel pretty good about that because that would really mean it's like from 41 to 45. And that's a pretty small interval. But because it's a small interval, it's also reduced the chance that my interval will actually cover P. Well, why don't I just make it bigger? Okay. What if I said it was 43% plus or minus 20%? Well, now I've made a huge interval. It basically goes from 23% to 63%. I've got a giant interval. There's a really good chance that my interval's big enough that it's going to find P somehow. But by making my interval so big, I've made it kind of useless. Like if you came to me and said, how am I doing in class? And I said, I think your grade is about a 70% plus or minus 3%. Well, that's a pretty good estimate, but it's also a small interval. And because it's a small interval, I might have a chance of being wrong. But if you came to me and I said your grade's 70% plus or minus 50%, I got a really good chance of being right, but I've given you useless information. So that little bit of wiggle room that we want to give to create that confidence interval, we've got to balance that against making the interval too large. And when we make it too large, it becomes a useless measurement tool, a useless estimator. Okay? So there's going to be a balance that we're going to have to find between being so small like this one, where there's a chance we're going to miss what we're looking for, and being so big like this one that it becomes a useless measurement tool. Okay? And what this boils down to is something that statistics calls the confidence level of your confidence interval. The confidence level is the probability that your confidence interval does what you said it's supposed to do. In this case, contains that population parameter. Right? Confidence levels are based on a percent chance, a probability that your confidence interval actually contains that population parameter that you're trying to find. Right? Standard confidence levels are 90s, 95s, and 99s. Technically, you could have anything. Someone could say, build us an 80% confidence level interval. We could. It's just not a standard one that most people do. We see lots of these 90s, 95s, and 99s. Okay? They are also sometimes referred to by their corresponding alpha level. Okay? And the alpha level for a 90% is 10%. But for some reason, probably to make it complicated and challenging, we express confidence levels almost exclusively as percents, and we express alphas as decimals. But essentially what we're saying is, if there's a 90% confidence level, then there's a 10% chance we're kind of wrongish. 95, 5%, 99, 1%. Do you see the parallels between those two numbers? Between those two numbers, they're technically complements. They add up to that 100%. If we had to speak in generalities, this is the most common one. It is very common to have a confidence level of 95%. So if someone came at you and said that they had a confidence interval of 43% plus or minus 7%, and their confidence level was 95%, what they're saying is that this interval, right, the 43% minus 7%, which would be 36% on the low end, all the way up to 43% plus 7%, that'd be 50% on the high end, that they feel that they are 95% certain, or that they have a 95% probability that that interval will contain the actual population parameter. Okay? Now, one thing to keep in mind, when we're talking about this population parameter right here, this guy, right, it never changes. It is where it is. Its value is set. This value, that changes. That p-hat, that estimator changes. Every single time you take a new sample, that estimator is going to change. Because where does it come from? It comes from a sample. That came from talking to 1,487 people. And if I talk to a different group of 1,487 people, I would get a different value than 43%. Now, hopefully, it would be close, but it definitely would be a different value. Right? All right, so let's take a look at the math that's going on to make this. Right? But before we do that, I want to just point out something. When we interpret our confidence intervals, or when we talk about them, we want to make sure we interpret them correctly. Okay? So let's say that we created a confidence interval that was this. That was 40.5% to 45.5%. And we were told that this is a 95% confidence interval, or a 95% confidence level for our confidence interval. We normally shorthand it to a 95% confidence interval. Okay? The correct way to say that, or to interpret that, would be that we are 95% confident that our interval actually does contain the true value. Right? So what we are saying is the value's out there, and I believe that I've got a 95% chance that if I put my value on the number line, my interval here, that I would actually capture P somewhere in that interval. Right? An incorrect way or a wrong way is to say that there's a 95% that the true value of P fall between. Because this statement implies that our interval is fixed and then P is going to get put somewhere in the interval. And it's the other way around. P is fixed. We're putting our interval on the number line and we're saying, did we get it right? Right? It would also be wrong to say that 95% of sample proportions will fall in that interval. And that's just not correct, because that's saying if you ran the experiment again, there's a 95% chance that your results would be in that interval, and that's just simply not true. Right? What it is trying to say is that if I did the same thing again and again, a confidence level of 95% tells me that if I ran the experiment again and again and again and again and again, about 95% of the time, I should see my interval capturing that true value P. So if we think about it this way, assume, and I don't know what the answer is, but assume for a moment that P is exactly 50%. Every single time I run the experiment, survey 1,487 people, get their results, get a p-hat for each different experiment, create a little confidence interval around that p-hat, put it over here on this number line, and is P actually in the interval I made? Well, according to the math, a confidence level of 95 would mean that 95% of the time that's true. Or approximately 1 out of every 20 times, our data would create an interval that actually wouldn't capture P. Right? So that would be this guy, right? Now, this image is from the textbook, and I am not quite sure why they made the ones that did it right red and the one that was bad green. I would have thought they would have flipped those colors and made the green the good and the red the bad, but hey, whatever. This is their stuff. Right? So there's the basic idea. 95% confidence level tells me that if I repeat this experiment again and 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 again, every single time I'm going to get a different interval because my data is different. But if I've sampled correctly, and we're assuming we do, most of the time, in this case 95%, my interval will do its job, and it'll actually capture the true value P. Change that from a 95 to a 90, then you're looking at 9 out of 10 are good, 1 out of 10 is bad. Change it from a 95 to a 99, then you're looking at 99 out of 100 are good and 1 out of 100 is bad, that kind of thing. Right? Right. Essentially, what we're doing here is we're working with things called critical values. And critical values are numbers. A critical value is a number, but critical values are numbers. On the borderline separating sample statistics that are significantly high or significantly low from those that are not significant. Right? Now, how we're defining significantly high or significantly low depends on what's our alpha level. So if I were to say, let's make an alpha level of 0.10, which corresponds to a confidence level of 90%, what we're saying is make this in here 90% and make each of those tails 5%. Now, where did 5% come from? Well, if there's 90 in the middle and this interval is symmetric so that this value is negative z alpha divided by 2, right? Interval is symmetric, curve is normal. If 90 is in the middle, then the other 10% is the two tails. Now, if I change that and make an alpha level of 0.05, which gives me a confidence level of 95%, now those two tails are no longer 5%, And that middle is no longer 90. The middle is now 95%. And this tail over here on the left and this tail over here on the right are 2.5% and 2.5%. And then we would just calculate these values, these critical values. Those are those cut scores, if you will. Right. Now, if you went crazy and did the alpha level of 0.01, which is a confidence level of 99%, then in the middle here, we're looking at 99%. And the tails over here then get really small, right? Because we only have 1% to share between both of those tails, which means this one over here is 0.5% and 0.5%. Now, hopefully something that you're noticing here is as the alpha level decreases, 10% to 5% to 1%, or correspondingly, as the confidence level increases from 90 to 95 to 99, this interval here in the middle is going to have to get wider and wider and wider, which creates a wider and wider and wider confidence interval. And if my confidence interval gets too wide, as we talked about a moment ago, it starts to get useless. Like, what good is it if I tell you that the interval is 70% plus or minus 25%? Because remember, it's plus or minus right here. So that really means that the spread of this interval ends up being a 50% interval. A 50% spread, I'm sorry. And then you're looking at it going, who cares? That's so big of an interval that it becomes useless to me. It doesn't give me enough accuracy. So one of the most challenging things about confidence intervals is trying to balance having a high enough confidence level that the faith in the interval is good, but having a low enough confidence interval so that the error, that plus or minus business, is small enough to make it useful. Okay. All right. How does one find critical values if you need them? Well, we find critical values by using that normal distribution. If we know how much is in the middle, we can find those tails. We can work things backwards like we did in the chapter on normal distributions. We would use that, what was it, inverse norm command to find those. And we could establish that this one over here is found by having the area to the left be that. And then this one over here could be found by having the area to the left be all of that. Meaning that it would have to be the 95 in the middle plus the 2.5 on the end, or 97.5%. And then we would grab our calculator. Let me move it over here to the side. Right. And we would go to our, our distribution menu and do our inverse normal command. And we want that to be 0.975, mu1 standard deviation, mu0 standard deviation 1, because we're working with z-scores here, so standard normal. And do you see the negative 1.96 rounded to 2 decimal places showing up? So that's where that 1.96 is coming from. Now the reality is we pretty much stick with these guys right here. And so it wouldn't be in your worst interest to kind of memorize those. You'll see them enough where you might just end up memorizing those just because you've seen them enough. Worst case is you can always build them every single time, or you can memorize them. A 90% confidence level, 1.645. 95 is 196. 99 is 2575. All right, we're at 25 minutes. I'm going to stop this one here. I'm going to come back, and when we come back, we're actually going to start calculating margins of error. I'll see you all back here for part 2.